Anastasia, floor is yours.
Thank you, Chiara. Thank you, Gerardo, for inviting me to be a part of your seminar. And it is my pleasure to present the ongoing project conducted with my co-author, Liu Shu. We worked on it in Grand Sasso Science Institute, where I'm a postdoc now. And the topic of our research was the current fluctuations of totally asymmetric simple exclusion process within a periodic environment. The project itself was inspired by the questions posed by Stefano Ola. And as a part of answer to these questions, I present today the scaling properties we found. Okay. Yes, if you're interested on Archive, you can find the manuscript, but it is very detailed. I'll not show you all the details today, just the main ideas and the motivation part. Well, to begin with the motivation, TASEP is a totally asymmetric simple exclusion process. It is a fundamental model of non-equilibrium statistics. And despite its simplicity, this model helps to understand quite complicated phenomena such as clustering and pattern formation. The model itself belongs to Cardar-Parisi-Jean universality class. It means that it shares the same universal scaling laws and the same fluctuation statistics as it was found for the Cardar-Parisi-Jean equation. While the stationary state for the TASEP is very well understood, there are still the open questions about the spectral properties which dictate the relaxation behavior, the current fluctuations, and also the rare events characteristics, especially in finite systems. All of these things I said, they remain less explored. For today, the plan consists of 3 parts. In the first part, I'll start from definitions, where I define and motivate why we need to study current fluctuations. In the main part, I'll present you the method, which is called Bethe ansatz. It allows us to find exact expressions for the eigenvalues and the eigenfunctions. And then in the final part, the last one, I'll show you the results we found. The first part is the finite size results for the system of finite size, and then the results obtained in the asymptotic limit when we're going to consider the systems of large sizes. Okay, to the first part immediately. We define a totally asymmetric exclusion process on a ring where this is one periodic lattice with n site. Each site can be occupied by at most one particle. In total, there are p particles. The model evolves in a continuous time, which means each particle has an independent exponential clock of rate 1. When a particle's clock rings, it jumps to the neighboring right only if it's empty. The configuration space denoted by omega and p, and each configuration is a set of occupation numbers eta 1, eta n, where eta I could be equal to 0 if the state is empty, and 1 if it's occupied by a particle, and then the total number of particles is preserved under these dynamics. Now, to describe the dynamics, we introduce the probability for a system to be in a state eta at a given time t. For a given initial distribution, the model evolves in a continuous time according to a master equation, where the equation describes the changes probability is expressed in terms of the difference between the probability to be in a state eta where 2 occupation numbers on the position x and x minus 1 are exchanged, minus the probability to be in initial state. And from this master equation already, you can see that it's very easy to understand what is its stationary state. Indeed, if this right-hand side, if every term on the right-hand side is 0, which is achieved when all the probabilities of all states are the same, then you found the stationary state. But since we're working in a finite size environment, you can introduce PT, the probability distribution vector. So what you do, you take PT of eta for each state, and then you combine it in the vector. Then the master equation can be rewritten in a matrix form, where PT is a vector and M is a transition rate matrix, so that the sum over all rows and also columns is equal to 0. Then for the matrix M, we can apply the Perron-Frobenius theorem, which proves that the matrix M has a unique eigenvalue of the dominant magnitude, which for the transition rate matrix is 0, and the corresponding eigenvector can be chosen positive. This is exactly our stationary state, and the uniqueness of eigenvalue also guarantees that this stationary state is unique. Okay, now to the variable of our interest, observable, which is called the total particle current, denoted by y of t. Fix the initial value, y of 0 equals 0. Then denote by y of t the random variable over the trajectories of the process, which calculates the total number of jumps up to time t. Introduce this joint probability pt small for further purposes as the joint probability to be at state eta at time t, and at the moment t perform exactly y jumps. Then, in terms of this joint probability, you can define the moment generating function. The moment generating function itself is a natural way, a natural thing to analyze in order to extract information about the behavior of the total particle current as a random variable. So for this purpose, we define this function, the moment generating function, restricted to a final state eta as gt of eta, which is just a linear combination of being in a state eta at time t, performing the number of jumps y, multiplied by the exponent in power gamma y. Gamma is a parameter of the moment generating function. Then, if you try to understand how this moment generating function evolves, you realize that it also satisfies to an equation. And this equation, we called it a deformed master equation, because it looks exactly like the equation for the probabilities, with the only difference that there appears the parameter E gamma, which you can also think of as a tilt. And therefore, when we write down the master equation in a matrix form, we're dealing with not with the transition rate matrix, but we're dealing with the tilted transition rate matrix M gamma, where in all elements which are known on the diagonal, you have, instead of 1, now you have parameter E gamma standing. And you can continue with the same idea as before. M gamma has negative numbers only on the diagonal. And this negative number is a sum of these etas. So the negative numbers on the diagonal is from -1 to -p. Therefore, M of gamma is almost, if you add p times identical matrix, then you'll have on the diagonal non-negative elements. Therefore, for m of gamma, you can also apply the Perron-Frobenius theorem. And you can guarantee that it guarantees that there exists a unique eigenvalue lambda 1 of gamma of largest magnitude, and the corresponding eigenvector could be chosen also positive. Okay. That's it. For here, that's it. Okay, now, coming back to the unrestricted moment generating function, in order to have the whole moment generating function, you need to sum up your function jt of eta over all final states eta. Here, the second formula is the result of the solution of the master equation, and when you write it, you realize that the solution of this equation is indeed just a matrix exponent, gt equal to exponent in power t m gamma multiplied by j0, but j0 at time 0 is p0. Therefore, this second form of a moment generating function follows. Now assume that you'd like to analyze the moment generating function. Then assume that for this matrix M gamma, you managed to diagonalize it completely. Then the matrix exponent here could be presented in the following way, so that the moment generating function is nothing but a sum over all possible eigenvalues multiplied by some numbers. So here, lambda I of gamma are the eigenvalues of the matrix M of gamma. And these A1, A2, and so on, these are some constant depending on the eigenbasis of the matrix M of gamma itself. For us today, the goal gonna be to analyze the spectral properties of matrix M at gamma, because these spectral properties indeed, they define the behavior of the moment generating function, and as it is, they define and describe the behavior of the total particle current as a random variable. Okay. Now, let me say that the literature on this topic is really vast and large, and there are three main regimes to study. The first one, the most studied one, is a large time regime. In this case, the exponential growth rate of the moment generating function is given just by the largest eigenvalue of m of gamma. Indeed, the dominant term of the decomposition I showed on the previous slide. So if you take your moment generating function, then you take logarithm and you scale it by t, you'll see the largest eigenvalue lambda 1 of gamma, which is unique according to Perron-Frobenius theorem, and it will define the behavior of the whole moment generating function, and it will define the scaled cumulants called Cn. If you'd like to think about large deviation function, then I would like to remind you that the Legendre-Fenhill transform of lambda 1 of gamma indeed gives you the large deviation rate function. Then the second thing to describe the large time behavior is the convergence rate of the moment generating function when time goes to infinity. The convergence rate of this expression is controlled by the spectral gap of m of gamma. By spectral gap, we understand the difference between the largest eigenvalue, lambda 1 of gamma, minus the second largest, lambda 2 of gamma. Indeed, if you write down the logarithm of moment generating function and then you scale it by t, you'll see the dominant term lambda 1 of gamma plus the remaining terms, which as t goes to infinity can be controlled by this exponent. Therefore, from this expression, we already see that there will be a relaxation time, which is going to describe the longest convergence time to the uniform distribution, or, in other words, the slowest convergence rate of the system to the uniform distribution. And the last, but at the same time the most complicated analysis is usually given for the short time. And it is complicated because short time is very sensitive to the initial and final states, and you'll have a lot of things to keep in mind here. Okay. Now let me describe you a little bit the results that were already obtained, and as before, I'll start from the large time, where the usual approach is to use the Bethe ansatz and additionally the geometric solution structure. And this is how the relaxation time was estimated at first with the Bethe ansatz, the spectral gap lambda 1 when the parameter gamma was 0 minus lambda 2 of 0 was found to be n in power minus 3 over 2. Therefore, the relaxation time is n in power 3 over 2. It describes the longest convergence time to the equilibrium. First, this result was found at half filling by Li Hun Gua and Herbert Spohn. Then it was generalized to arbitrary density by Docciuli, Kim, and collaborators, and also by Olivier Collinelli and Kieran Malik in a series of papers. Moreover, the same method allows to get the whole large deviation function and additionally the exact scale cumulants, including the diffusion coefficient. Then, for the analysis of the relaxation and short times, here the system can still keep the memory of the initial state compared to the large time. And this is the place where the usual approach is to use the non-stationary transition probabilities. These probabilities are given for example, for an open system on Z, these probabilities are given as a determinant. And usually it's very hard to deal with, but there are still very nice results due to the fact that for these determinant probabilities, nevertheless, you can use these formulas in order to get, for example, joint probability distribution in terms of Fred-Golomb determinant representation, and then this Fred-Golomb determinant representation allows you to perform asymptotic analysis. This was done by Günther Schutz in paper 1997, but not only. Then let me also remark that the most intriguing thing in this story is that it was found that the TASEP itself is connected to the random matrix theory, which follows from the paper of Kurt Johansen, who connected the dynamics of TASEP with the problem of the longest increasing subsequence in random permutations. Okay, to summarize.
Sorry, can I interrupt you?
Yes.
Yes, in all these works, could you specify what is mathematically rigorous and what is not rigorous? For example, the result of Gua-Spohn is not rigorous. No? Or yes? I think, this paper of Johansson, Beck, Reins, Spray for Spohn, I think they are rigorous, but the previous one, I'm not sure that they are totally rigorous. So, do you know? Or?
Okay, I think I understand your question. well, I believe that the paper of Gua and Spon I'm referencing here is considered to be rigorous. The question that the issue that can make okay, the issue which is important here is that when you analyze the spectrum of the matrix M of gamma, there is I'll tell you more about this later, but there is an issue, for example, how to find, for example, for the largest eigenvalue, you're sure that it's unique, and and then what is done there is a continuity argument. So at first gamma is kept really small, and then in the neighborhood of gamma small, you know that since gamma introduced in matrix M of gamma continuously, then largest eigenvalue should continuously change with the parameter gamma. Then during this analysis, you use this continuity argument. However, for the second largest eigenvalue, you cannot be so sure. You cannot say that you cannot guarantee that the way you define the second largest eigenvalue is indeed delivering you the right eigenvalue. Because, for example, varying the parameter gamma, second largest eigenvalue could merge with the third one, and now the third one becomes the largest one. So with this argument, you should be very, very careful. However, for in the limit of which is done here, this is considered rigorous. Yeah.
Okay, because at least this paper of Derrida, I think they are not rigorous. I don't know, maybe I am wrong, but I'm not so sure that they are rigorous papers. Okay, I don't want to disturb you, but okay.
If we can discuss later.
Yes.
Yeah, this is a very good question, and I'll say you more about it.
Okay.
You're right.
Thank you.
Yeah, thank you, Cedric. This is a very good question. You're right. You're right. Yes, it sounds very nice when I describe it like this, but then you very right. There are very serious issues once you try to make everything rigorous and strictly, yeah, and when you try to prove it. And I'll have also these issues. I'll show you. Okay, let me. Okay. To conclude with, now we will focus on the study of the largest eigenvalue of the tilted matrix M of gamma, and also we'll study the spectral gap of the matrix M of gamma, allowing gamma to be finite. And we believe that these results are gonna get us the understanding of the behavior of the total particle current beyond the stationary state regime. Okay. Now I would like to jump to the second part of my talk and tell you more about the coordinate Bethe ansatz. But before it, let me show you the preliminary results, which gonna gives us the bounds for the largest eigenvalue. So up until now, n is fixed, p is fixed, M of gamma is a finite size matrix, and the bounds you can get as a consequence of the Piron-Frobenius theorem are the following. The largest eigenvalue, you'll find that this is, well, first of all, since gamma introduced inside the matrix M of gamma continuously, then lambda 1 of gamma is the monotone increasing continuous function of gamma. And then you realize that for gamma negative, lambda 1 belongs to a negative interval given in terms of, belongs to a negative interval given in terms of gamma here and p. Then for gamma positive, largest eigenvalue belong to the positive interval. And then if you picture the spectrum of the whole matrix, you realize that the case of positive and negative gamma are different from each other as a whole. So the whole spectrum behavior is a little different, And later I'll show you more pictures and explain what we observe and how we can use this for description of current fluctuations. Okay. Okay, now we jump to the heavy machinery, which is the coordinate Bethe ansatz. And this is the particular feature of the integrable models that they allow you to represent their solutions in a particular form where the property of integrability gives you the exact formulas. So now we use the following notation for the particle position of coordinates. Before we used eta, but now this eta we denote it with coordinate representations, where x1 is the position of the first particle, x2 the second one, and so on. And these x's are from 1 to n. Each component of the eigenvector labeled by the particle coordinates is represented as a linear combination of three ways, where summation is taken over all permutation of this zeta in power x I, and these zetas in this ansatz are until now arbitrary complex numbers, but non-zero. Then from the spectral equation, you'll find that the largest eigenvalue is given by the following formula if and only if the complex numbers zeta1, zeta p satisfy the following Bethe ansatz equations. I'm giving you the short version here. So the Bethe ansatz equations is a consequence of the two things. The first thing is it follows from the periodic boundary conditions, right? So we accounted that if we rotate our coordinates by one position, then it should be if we rotate by n, then it should give us the same phi. Plus, additionally, we consider the two particles standing nearby, and I'm shortening here a little bit just to give you the final results. So once again, we'll find that largest eigenvalue could be found in this form if the zeta1, zeta p satisfy the set of Bethe ansatz equations. So here we have a system of p equations. And usually this is very hard to deal with, these equations. They are non-trivial to solve. But for the case of TASEP, the Bethe ansatz equations decouple. Let me explain you more precise what does it mean decouple. To make it more visual, I'll use new variables called zeta j, which is shift plus inverse of the original. Then the largest eigenvalue takes a particularly simple form, which is just the sum of zeta j. And the Bethe ansatz equations are rewritten in the following form, where the right-hand side, if you look on the right-hand side, is given by the same formula, by the same expression for every equation. Indeed, it's the product over all j from 1 to p. Therefore, this right-hand side is the same for every k. The idea how to deal with these equations is the following. Imagine that you have solution given by a set of zeta1, zeta p. If you have solution, then they all these zetas satisfy to the same polynomial equations. Indeed, since you know the solution zeta1, zeta p, you calculate this right-hand side as a product over all zeta j, and then each zeta satisfy this polynomial solution. 1 minus zeta k in power p multiplied by 1 plus zeta k n minus p equal to some constant. Okay. Yes,
sorry to interrupt you again, but if this is for the TASEP, if it is ASEP, this doesn't work, or does it work?
Unfortunately, no.
No,
This
it is
particular
particular.
feature of TASEP, indeed, equations decouple. Yes, in the ASYP, yes. Yeah, in the ASYP, this form will be more difficult. It will include zeta k, zeta j as a term here, with the parameter q, and unfortunately, it won't work. Yeah, it won't work. The thesis. So it would be nice to generalize, but maybe we will need some additional ideas. Yes.
Okay.
Very good remark. Thank you. Thank you, Cedric. Okay. So we realize now that if we know the solution, that every element of this solution belongs to the same complex curve. Since we cannot picture this curve in a complex plane, in a complex space, we'll consider the absolute value of this curve, which is known as a Cassini curve, and given by the following equation: y minus zeta, absolute value in power p, 1 plus zeta, absolute value in power n minus p, and the right-hand side is some constant, which we parameterized as r in power p. This right-hand side is called the focal radius. The focal radius r will define the geometry. Indeed, easy to see. When r is 0, your curve is just 2 points, 1 and minus 1 here. Then, if rho is less than rho critical, the curve becomes 2 ovals. One oval on the right encircling 1 with exactly p points on it, and the one oval on the left encircling minus 1 with exactly n minus p points on it. Then, as r increases, these two ovals merge into one curve and they form lemniscate. They form a deformed lemniscate of Bernoulli. And then, when rho is more than rho critical, we have one oval. The asymmetry you see in the curve, this depends on the density. So the density of the model we consider will define the asymmetry of the oval curve, of the Cassini curve. Okay. Okay, this all said, we will tell how you can solve Bethe-ansatz equations when they decouple. So now, when they decouple, we perform this strategy called backward strategy, inspired by the approach of Oliver Golinelli and Kieran Malik, where they suggested that you can solve it if you select p solutions out of n. Indeed, to solve p equations for p variables, the one we have, we were looking for p points. So the first step we select p points because we need only p, but possibilities we have, there are n. So let's introduce the choice function L and label the points we choose. For example, we would like to choose the rightmost p. So we'll label them with some indexes and fix. Now, once you've did it, you can define the points you've chosen as a function of a parameter Cn gamma, where Cn gamma is the parameter, is in general complex complex parameter defining the size and the geometry of your Cassini oval. Once you've expressed this formally as some points depending on the parameters, then you remember that that these points, they should belong to the same curve, plus the Bethe equations should be satisfied, which means that the parameter defining the Cassini oval should satisfy the consistency equation. Indeed, this Cn gamma was the right-hand side of Bethe-ansatz equations, and it was denoting these expressions in terms of zeta j. So the points, this zeta j is the points we've chosen. So now instead of zeta j, we put our choice UL of C here, and then we solve these equations in order to find C and gamma. This is the backward strategy. But I think you already have questions, but before the questions, let me say that the strategy itself has its limitations, and it's not clear a priori that the method like this is complete. I mean that it's not clear that all the eigenvalues and all the eigenvectors can be delivered in this way. It's still an open question, and here, for example, the recent results for the TASEP are about the Bethe ansatz completeness, which says which is the following result. Bethe ansatz equations we've seen now, they has exactly P chooses n physical solutions calculated with multiplicities. Therefore, the system of Bethe ansatz equations indeed potentially can generate all solutions. However, the backward strategy still will have this limitation of completeness. The paper I mentioned is by Aivao and Motegi of 2025. Then the second problem we're dealing with is the correct defining of a choice function. Which choice of the points you should take for the largest and next to the largest eigenvalue? Which p out of n points to choose? This is not obvious, and there are many choices. And interesting remark is that when we analyzed it, we already found that not every choice function delivers you a solution. We found an example where this is true, and I'll also comment on it. You'll also see that this is a very pretty obvious to note. Okay, to overcome the second problem, the correct defining of a choice function, so the analysis of the largest eigenvalue in the spectral gap requires me to correctly define a choice function for the largest eigenvalue for the second largest one. And to overcome this difficulty, we formulate the following assumption inspired by the paper of Liu Honghua and Gerbert Spohn, and also by Bernard Derrida and Christoph Appert. We assume the following: that for sufficiently large n, the largest eigenvalue lambda1 of gamma is indeed achieved by selecting the rightmost p point on the Cassini oval, and the indices we give them is from 1 to p. Okay, on the pictures you see 2 out of 3 possibilities for the Cassini oval. Because a priori we don't know how it looks like. On the left you'll see 2 ovals, and in case of this is 2 ovals, we just choose the p rightmost points on the right oval. That's it. Then there is the case of lemniscate and the case of 1 oval, and here the assumption is the same, p rightmost points, but now they belong to the same curve. So for the analysis to perform, we introduce the separating curve drawn here by dashed line, and it separates the rightmost p points on the Cassini oval from the remaining part. Okay, then we continue with the assumption for gamma positive, but for the second largest eigenvalue. So the assumption is the following: that second largest eigenvalue is delivered by a minimal modification of the previous choice. So now we don't take p rightmost point, we take only p minus 1 rightmost point, and then we choose 1 rightmost point from the remaining part. So here, instead of u5, we'll take u12 on the left picture, and then in case of 1 oval, for example, instead of u1, we'll see u12. We'll take u12. Of course, this choice is not unique, but as you remember, the matrix we analyze, M of gamma, it is real, and we know that We know that the eigenvalues, they can come in complex conjugate pairs. So although there are 4 choices in this case, in the end, it will this assumption will result in only 2 choices. But okay, the following analysis well, includes all of these choices. Okay, now interestingly, that for gamma negative, the assumption we used before doesn't work. So then we suggest the following. For sufficiently large n, the largest eigenvalue lambda1 of gamma is achieved by the choice of the p-1 rightmost p point and the rightmost among the n-p leftmost point. So in this case, this is indexed by okay, so the index I put here is for the 1 oval. And okay, I promised you to explain why why we need to change our assumption. You can conclude it from the following thing. I think you remember that we said that there are bounds for the largest eigenvalue, and for the gamma negative, lambda1 of gamma should be negative. Therefore, consider the density, which is very small but finite. In this case, your oval will be very asymmetric one, and then this dashed curve will become very curved to the right one. And then your points, when n becomes sufficiently large, these points, they start to fill in your Cassini oval, but they fill it uniformly. So there will be points almost everywhere. And then all these points, they will take the rightmost part of the Cassini oval. Or they will take, or they will fill the whole right oval. And if you analyze carefully the equations, you'll see that with the choice of the p rightmost p points, you cannot have a negative largest eigenvalue for n sufficiently large. So there is this contradiction. Okay, for the second largest eigenvalue, we continue in the same manner. So we say that we need to perform a minimal modification of the choice done above. So now again, we will keep p-1 point on the right, but now from the leftmost point, we'll take not the rightmost point, but let's say the next one to the rightmost. Okay, let me show you now the finite size result, which follows after performing the backward strategy and the assumptions we discussed. So the finite size results are implicit, and they are given as a result of the Bethe ansatz solution here. So we find that the largest eigenvalue lambda1 of gamma is given as a sum of the points uj of the Cassini oval, where labels corresponds to the rightmost p points. Then the second largest eigenvalue is p-1 rightmost p point, and 1 point which is rightmost from the leftmost. And the parameter of focal radius of the corresponding Cassini oval should be defined from the corresponding consistency equations. So since I cannot solve these equations well, exactly, so that's why I call them implicit finite size results. Okay, what is more valuable for us is the asymptotic result, which shows you that there is a phase transition in the behavior of the largest eigenvalue. So what you do, you say, let me take p and n going to infinity. Let's fix the density fixed, and then we see that the largest eigenvalue experienced the phase transition, precisely going from inactive phase, which is described by the fact that the main term in the asymptotic decomposition will be this universal value -1. So it is inactive for gamma negative, and then for gamma positive, the largest eigenvalue is growing with n multiplied by some model-dependent constant lambda of gamma rho. Below you can see that lambda of gamma rho is given by some complex, by some complex valued function of a parameter, and behind the definition of lambda of gamma, there is an asymptotic analysis done for the exact results you've seen before. Okay, let me, for the completeness of the picture, show you very shortly the sketch of the proof of theorem 1, which is the following. So you introduce the new functions, which represent the sum over all uj of C, the points lying on the Cassini oval. Then you can rewrite the consistency condition in the following form. And then you can take the logarithm of this consistency condition. You estimate the obtained sums over uj with the Euler-Maclaurin formula, in which you control the error terms. And then the consistency condition, which is gamma equal to, in the limit n to infinity, the right-hand side becomes some function g infinity. You can show that when n goes to infinity, the asymptotic equation has only one solution, which is r star more than critical. So this is one oval. The limiting curve for gamma positive is one oval. And then you'll see that the largest eigenvalue is indeed growing like n, scales like n in the dominant term. Then for the gamma negative, you'll see that there exists rho star less than rho critical. And then from here, from the assumption that you've done before, you'll conclude that lambda n scales as -1 plus some error term. So this is the sketch of the proof. Where I omitted the whole careful analysis of considering every possible case of Cassini oval and parameterizations we used. Then let me just conclude with the result number 2, where you'll also see that the same asymptotic, the same phase transition you can also see in the behavior of the spectral gap. So spectral gap for gamma positive, it closes linearly with n. So it behaves like 1 over n, and then it decreases exponentially fast when the gamma is negative. So these are two completely different behaviors. To assure you even more, let me also show you the pictures, the numerical simulations, which demonstrates you this one is done for gamma positive, gamma equal 1. And you'll see the whole spectrum of the matrix M of gamma changing with n. So starting from n3, then 6, 9, 12, you'll see that the spectrum itself forms like kind of an avocado. And then the rightmost point, now if you look at the rightmost point here on the peak, it moves to the right with n growing. And the same is for the lambda 2. So both lambda 1, lambda 2, they grow with n, and then, but the spectral gap closes like 1 over n. Then for gamma negative, picture is completely different, but what you can see is that the largest eigenvalue next to the largest eigenvalue, they with n growing, they become smaller and smaller, and they sit here on -1. So first you see there is a small loop around -1, and then with n growing, more and more eigenvalues concentrate there, and this is it. So that this is the exponential closing we observed in our results before. Okay, and let me conclude with the 3 points that we discussed today: the Bethe ansatz for the TASEP, which gave us implicit expression for largest eigenvalue and for the spectral gap. And the largest eigenvalue we got, it matches with the results of Bernard Derrida and Christoph Appert, although it offers a distinct representation. Then what we observed is a phase transition in the thermodynamic limit. Let's shortly say that it changes for gamma positive from active phase to the frozen phase. And the spectral gap closes linearly for gamma positive, and close exponentially fast for gamma negative, indicating on the presence of beta stability. And there are still the open questions that Cedric mentioned, like extension to the ASEP. But as I said, you need some more techniques or maybe very careful analysis. This is still open for me. And then refine finite size corrections. Very interesting could be to find connection to Riemann surfaces, which were employed in the proof of completeness and also in the series of papers of Silva and Pralahak. And then the cherry on a cake could be dynamical large deviations, which could be both time-dependent or path-dependent, as well for the particle current and as well for any other observables. So still open. Thank you very much for your attention.
Thank you very much, Anastasia. So let's see if there are questions or comments from the audience.
So in your result, okay, in your two theorems, you have asymptotic behavior for fixed gamma.
Yes.
Do you know how things like behave? Like how does it transition from the negative behavior to the positive behavior when gamma is small? Do you see something? Do you have any estimate on how it interpolates between these two regimes? Like perhaps, okay, do you know how this gamma, no, is it a lambda or gamma? Lambda. This lambda of gamma rho, do you know how it behaves with gamma at 0 or? Like how do you transition from this -1 to n in between?
No, this is, I don't know. This is a good question. Yeah, I don't know.
And in theorem, okay, also in theorem 2, you know, you have this n-1 appearing, okay, on the positive side. And when you are equal to 0, you have n to the -3/2. So when gamma goes from positive to 0 in between, do you know how it changes from n to the -3/2 and n to the -1? Okay, and perhaps also what's the interpretation in the, what does this n-1 means compared to the n-3/2 you have in the gamma equals 0 case? Okay.
Okay.
But sorry, Hubert, do you mean that it is something related to the cutoff phenomena or?
Yeah, no, I was wondering, like this n to the -3/2, it corresponds to the relaxation time of the system. This
Yes,
n to the -1/2, does it correspond to something of the, once you are considering the current, or?
Well, okay. Okay. Let me come back to the M of gamma. Maybe I can explain you that here, the M of gamma. So since we're analyzing this deformed M of gamma, now the generator, the matrix we're analyzing, it corresponds to a tilted generator. So for gamma positive, you in some sense you encourage if your system makes jumps. So in terms of mixing times, I believe that this system is mixing very fast, and it gives preference to the states which produce huge current. So it could be well, the favor will be given to the states with p clusters, with p separately standing clusters. Then for gamma negative, we can interpret that now we tilted the generator, and now we are punishing any jump done, and in this case we favor the frozen states. And I believe that this is what we see in the spectrum, that this spectrum which condensates around -1 and -2, it exactly reflects this frozen behavior. I'm not sure we can say we can interpret this as a convergence time, you say. Let me see. Yeah, okay. Okay, I believe you can use the same interpretation in terms of the convergence time, but then you should say that the thing you analyze is a tilted generator.
Okay, thank you, and sorry for making my question very confusing.
No, thank you for the questions. No, to be honest, I don't know. There should be scaling functions interpolating from one regime to another regime. And maybe one more comment I can make is that when you consider gamma around 0, then you realize the following thing. So when gamma equals 0, all the points they concentrate. Let me come back to the case of picture with Leibniz scale here. So for gamma equals 0, the solution what is done? You consider the gamma small but around 0. And then you realize that all the solutions of Bethe equations, they condensate on the Leibniz scale. So the thing we observe that this phase transition makes the following. So for gamma positive, now instead of Leibniz scale, you are on a big green oval. So limiting curve becomes the green oval. But then when gamma was 0, all the points were on the right loop of your Leibniz scale, and then exactly one point was on the intersection, on this double point of Leibniz scale. Then what happens when we take gamma negative but finite, after we take the limit n very large, we observe the following: that one point which was here on the double point of Leibniz scale, it splits from the right loop, and now it happens to be on the left oval, while the remaining p-1 are still on the rightmost part. Well, yes, since I analyze, I should say that these limits, we should be very careful. These limits cannot be interchanged very easy. So the limit gamma to 0 and then to infinity, we should be very careful which one take first, and also the scaling. But the thing you observe is this continuity argument. So I believe that maybe if we analyze topology of the curve standing behind, then it gives us more understanding of how it's behaving in general.
Thank you very much.
Thank you.
Are there more questions or comment? So Anastasia, it seems to me this coordinate Bethe ansatz heavily relies on having periodic boundary condition, right, at the level of particle system. But so you have open boundary condition, I imagine it is more complicated, but what about closed boundary condition? Does it apply? Or you really need the periodic?
By closed, you mean on the interval?
Exactly.
Where you start from initial state, and then there will be some mixing. You say, okay, but for this model, you'll just start and then you'll just finish. I think.
Right. Yes, that doesn't make any sense. Yeah. You're right.
But if you introduce open boundaries for some, with the open boundaries, you can use algebraic ansatz.
Algebraic Bethe ansatz.
Algebraic Bethe ansatz. Yes, it will give you the stationary state, and yeah. I think you can perform this one.
Okay, thanks. Okay, so if there are no more questions.
Related to the question of Chiara, I think that there is some papers of Nina Ganter, which was considering the ASEP with reservoirs. And she was computing something about the spectral gap and some cutoff. I don't remember exactly, but this is maybe some paper to look at.
For the cutoff, For the cutoff phenomenon, there is the recent paper on TASEP. There is no cutoff phenomenon for periodic case, but for the interval, there will be cutoff phenomenon.
Yeah. Okay, and there is some other papers that I don't know how it is related with what you are presenting. Is some quite old paper now by Seturaman and Varadan about large deviations of the current. You know this paper or no?
I'm not sure.
Okay.
But if you share,
in fact, I don't remember. I don't remember exactly the paper. It is large deviation functions for the current. I think it's ASEP or TASEP. I don't remember. Okay, but okay.
Okay, yeah, but it was before. Well, the large division function in this case it is known. The question was posed for this tilted case when gamma is fixed. So it introduces a tilt. So the question we answer is spectral properties in the presence of tilt. Yeah, without the presence of tilt, indeed there is large division function. You can write it. Yes, I think. I don't know the paper of Varadan, but I'll look for it. Thank you.
Okay, thank you.
Okay, so I think there are no more questions. So thank you again, Anastasia.
Thank you.
And we see each other next Wednesday. Bye bye.
Thank you for the invitation. Bye.
Bye bye.
Bye.
For the
See you next
questions.
Wednesday.